Hi, we're Group 6 and today we'll present our task, which is the crosstalk canceller. Crosstalk is the unwanted electromagnetic interference that occurs between nearby parallel signal wires. It arises through two electromagnetic coupling mechanisms, which are electric field coupling due to mutual capacitance and magnetic field coupling due to mutual inductance. First, electric field couplings occur when the changing of voltage on the aggressor wire creates an electric field that couples an unwanted noise current into the victim wire. Meanwhile, for magnetic field coupling, the changing current in the aggressor wire produces a changing magnetic field, which induces an electromotive force in the nearby victim loop. According to Faraday's law of induction, this induced EMF is directly proportional to the rate of change of magnetic flux. In our experiment, the Arduino generates a fast 5V square wave as our source signal on the aggressor wire, while the induced noise on the victim wire is measured through analog pin A0. By modifying the physical geometry of the wires through spacing, shielding, and twisting, we can significantly reduce and eventually cancel the crosstalk.
We first tested the baseline configuration where the aggressor and victim wires were placed parallel and as close together as possible. In this arrangement, the result shows the highest level of crosstalk. Next, we gradually increased the spacing between the two wires. Measurements were taken at 0.5 cm, 1 cm, 2 cm, and 5 cm to observe the trend. As the spacing increased, both the mutual inductive coupling and capacitive coupling become weaker, meaning less energy were transformed from the aggressor wire to the victim wire. This resulted in a reduction in the induced voltage, decreasing from 0.819 volts in the baseline setup to 0.024 volts at 5 cm setup. Overall, the result shows that increasing the spacing between parallel wires is an effective method for reducing electromagnetic crosstalk.
The next improvement for reducing crosstalk is aluminum foil shielding. The aluminum foil was connected to ground, providing a low impedance path for induced charges. This reduces capacitive coupling between the aggressor and victim wires. As a result, the induced voltage decreased to 0.015 volts. The final improvement is twisted pair wiring. Both the aggressor and victim wires were twisted with their respective return wires connected to ground. From this diagram, each twist produces opposite induced effects, reducing the loop area and partially cancelling the magnetic flux. This significantly reduces inductive coupling and the measured voltage drop to 0 volts.
Now, let's dive into how these principles are applied in real life. In industrial automation, proper cable layout is crucial. Sensor cables are kept away from motor and power cables as they carry high current. The changing current can create electromagnetic field which can induce unwanted voltage into nearby sensor cables. Since the sensor signals are usually small, even small amount of noise can cause inaccurate readings which may lead to reduced system reliability. While for USB cable, shielding and wire twisting are both used to reduce electromagnetic interference and keep data transmission stable. From the picture here, we can see that there is a metal shield around the cable that blocks external electric field interference and sends unwanted noise to the ground. Inside the cable, the D+ and the D- data wires are twisted together so the external voice affect both wires similarly. Since the USB reads the difference between the two wires, the equal noise cancel out each other, helping the data signal to remain accurate.